Let's do some multi-agent programming now. In the last lesson, we saw already some simple examples of multi-agent programs, producer-consumer and producer-transformer-consumer, so simple pipelines. Pipelines are kind of really trivial. Let's look at some more sophisticated examples. And we're going to look at two examples right now. The first one is the sieve of Eratosthenes. And the interesting part about this example is that we're going to dynamically build a pipeline during execution. So we're going to add agents and we're going to build the length of the pipeline we need adaptively, exactly according to the need that we see during execution. And this is perfectly reasonable in the deterministic data flow paradigm, so it works very well. The second example is a digital logic simulation. So we're going to simulate digital logic circuits at a very high level of abstraction, and we're going to use some nice higher order functions as abstractions to help us build the circuits in a nice way. So let's take a look at the first example. So the first example is the sieve for Eratosthenes. We start with an input list, which is a list of integers. Usually it starts with 2 and it keeps going, 3, 4, 5. Our first agent is going to remove multiples of 2. So we call it the minus 2k agent. This gives us an output stream of only odd numbers. Then we remove multiples of 3 in a second agent. This gives us a stream with even less elements, and we keep removing multiples, 5 and so on, until we end up with a stream that contains only prime numbers, where a prime number is an integer that has as only factors 1 and itself. Okay, so that's the sieve. The way it works, we first need to define these agents that remove multiples. So the filter agents. So a filter agent, in fact, is just a list function that removes multiples of k. So we have here the function filter, which takes a list xs and a k. It then removes an element x from the list xs. It checks whether x mod k is different from 0. If it is, it passes it to the output. So the output is x bar filter xrk, the recursive call. Otherwise, it's not passed to the output. And this is just a list function, okay? It is an existing list function. In fact, it's even part of the system. We turn this list function into an agent by putting it into its own thread. So here we have an agent that has an input stream xs and an output stream ys. With this filter agent, we can now run the sieve program. So sieve here is a function that takes this list of integers. It removes the first element of the list, and the idea is that it will remove multiples of this element. So the x here will be the argument of the filter, and notice this thread end, filter xrx, this in fact is our agent that we are building dynamically. So it is the call, the recursive call to sieve is done here by creating the agent first and then doing the recursive call. So we call this also concurrent deployment. So we're deploying the system at the same time as we're executing it. We're building the infrastructure of a program during its execution. And here's the main call. So we do a first agent here, which is the good old prod agent from the producer from last lesson, which creates integers starting from 2, and then there's the call to sieve. And then we will just display ys, and this will display the list of prime numbers. As we can do a simple optimization, actually it turns out that most of the agents in this sieve program are not doing any work. The agent removing multiples of 2 does a lot of work. The one removing multiples of 3 does some work, and the farther on we go, the less work it does. But it turns out that some agents do actually 0 work. And in fact, it turns out the agents that are past the square root of the primes that we want to look at are doing 0 work. Because if an agent is removing a multiple of a number that is greater than the square root, then there's another factor which is less than the square root, so it's already been removed. If a number n is p times q, If p is less than the square root of n, then q is greater. And so the agent removing multiples of q does not do any work because the number has already been removed by the agent removing multiples of p. So we can make this optimization here by adding an argument m, and this argument m depends on how many primes we want. If x is less than or equal to m, then we would call as before, but if it's greater than m, that means we don't need any agents anymore, because all the agents we would create would not be doing any work. So if we want to create primes up to 100,000, we call this with an argument up to 316. And you see why that is.